In this lecture, we'll learn about surface adsorption and isotherms. As we all know that surface adsorption is one of the very critical phenomena in any particular processing or any particular catalysis activities. So in this particular place, we will define adsorption. Adsorption is defined as the accumulation of ions or molecules on a surface. As we know that it is one of the very critical parameters in terms of deciding the kinetics of a particular process, because depending on how many ions or molecules they get adsorbed on a surface, they tend to react, or they tend to form some species, or they tend to precipitate on the surface to result variety of properties. But again, it is different from absorption, because in absorption, volume of material, it holds the ions and molecules and not the surface. So in this particular process, we have absorption, in which the bulk of a material takes part in terms of attracting the species, whereas in adsorption, the particular species, it can be ion, it can be molecule, it stays on the surface of a particular substrate or an adsorbent. So in this particular manner, because once we have any surface being exposed to any environment, it is the surface which comes in contact first, and once surface reaction has occurred, then only it can go on further to the bulk, or in terms basically a volume of that particular material can take part in terms of dictating the subsequent phenomena. Again, in this case, in adsorption, atoms on the surface are not in contact with the adsorbent. So this is what that we have a free surface. So free surface, we have once we see the arrangement of particular atoms, and then we can see that the atoms which are not on the bulk, it means the atoms which are on the surface, these atoms, they now have free bonds, and hence they can attract the adsorbents to their sides. This is why it happens, is because the bulk material which has all the bonds satisfied. So bulk, we have all the bonds which are satisfied, whereas in case of surface, what we have unsatisfied bonds. So this becomes a high energy areas. So since it is high energy areas, definitely once we have any secondary species, they will tend to come and attract on the surface of this particular entity to reduce the overall surface area or the surface energy of this particular entity. Again, the adsorption can be defined as a physioption or a chemisorption. In case of physioption, we have particle which is trapped onto the surface, and once it is trapped on the surface, it is more like a potential well. So I have a particular entity which is entering the well by some means, and because of elastic collisions, the species can go back to the gas. So we have particular entity, particular ion or atom or molecule, it tried to go, but it could not because of elastic collision. It might try to come back, but it might also happen that upon collision it can lose all its energy. So it has lost so much energy that its energy basically comes down to a very lower value, and then it can just stay here without bouncing back. So in first case, once we have elastic collision, it goes, strikes a molecule, and then it comes back or goes to some other location without sitting along this particular side. But in this case, once it is losing all its momentum because of inelastic collision, it will remain stuck to the surface by some weak forces. Those can be van der Waals forces or London attraction. So this is being called as a physioption. So in this particular case, we have physioption. In physioption, we have particle which is now trapped onto the surface. So in this particular species, we can see that we have a zero potential. And then it basically now stays in the potential well for some time. So this is our so keeping it as a potential, and initially we have a zero potential, and then this is the surface of the adsorbent, and then we see the particular atom or molecule or ion, it comes and sits, and it basically gets entrapped into the potential well. So now it requires certain energy to get desorbed from the surface, and this may not happen in very quick succession. So the ion or the molecule can stay there for a little longer time, and this happens because we have elastic collisions happening with the particular molecule. So in case the molecule starts losing the energy via inelastic collisions, it might get entrapped into the potential well, which is now the surface of a particular material, and that second ion or molecule which is coming and striking the surface, now it is reducing the energy of the surface and that's why it is harder for it to go back, because it has lost all its energy in satisfying the inelastic collisions. So it remains stuck to the surface by some weak forces, which results in the physioption. So ideally this particular process has no barrier, because it is more like resting yourself on a particular wall so that you can lower your energy. So it does not have any barrier. It is more like a physical attraction, or the physical movement of a particular atom or a molecule to a particular surface site, and it is very fast, because in this case it wants to reduce the surface wants to reduce its energy. So whatever molecule or atom is coming on there, it is basically trying to get bonded with that particular species. So in terms of making it stuck on its surface, again these interactions are very they have pretty low energy. It is less than 0.4 electron volt. So that is what is happening out here, and they are always atomic or molecular in nature. And since there is no chemical bond which is forming out here, they are always reversible. At the same time, they are surface symmetry insensitive, because it is more like a physical movement of a particular atom to a particular location. So they remain insensitive to a surface symmetry. In case surfaces has some symmetry, they don't basically pick a particular symmetry in that particular sense. It may not want to go to a particular site, because they are not sensitive to the particular molecule which is sitting on the particular surface. And they can also lead to go on forming multi-layers, because if I have a particular species and secondary species come and sits on the surface, now that particular adsorbed species, now again it has some free surface available to it, so it can again keep forming some multi-layers, and the surface temperature has to be lesser than the condensation temperature, so that the particular species can lose its energy and it can stay on the surface for a pretty long time. So this is the overall deal with the physioption, that they don't have a barrier. The process is very fast, because surface wants to somehow reduce its energy, surface energy, and these are weak interactions of less than 0.4 electron volt, and they are always atomic or molecular in nature, because this has to happen by atom to atom or by molecule to molecule. And since these are only physical entities which are basically moving and going to rest on a particular surface, being held by some weak or van der Waals forces, so this is again reversible process, and they are insensitive to the surface symmetry. And since again this newly adsorbed species on the surface, again it will have some free surface available to it, so it can again keep forming multi-layers. And again for this to occur, the surface temperature has to be low enough, so that the particular ion or species, it can lose its energy, or it can lose its movement. So all the vibrational movements can be reduced by lowering the temperature. So surface temperature has to be lower than that of a condensation temperature, in order for the physioption to be much stabler for a little longer time. And going to the chemisorption is defined as a strong interaction. In the earlier case, in the physical physioption, we had weak interaction, but in this case we have a strong interaction between the adsorbate and the adsorbent surface. Adsorbent is where the overall substrate is. Adsorbate is the new species which is forming and sitting on the adsorbent. So in this particular case, we can define it like this, that this is a zero potential, and then we have some sort of a physioption which can occur. At the same time, we can also see the chemisorption is this is for the physioption, and this for the chemisorption, depending on the potential, and this is depending on the distance on the solvent surface, atom surface. It can be atom surface. So what is happening out here is that the closer it is going, initially with time, physioption will occur, because it has now much more probable that because of its lower energy, particular entity can go and sit on the surface. But eventually, for chemisorption, it is lowering down its energy by a much larger extent. So eventually, chemisorption is much more preferred once it can lower its energy by a certain value. So in this particular case, we have very strong the very strong bond which can form out here. So it has a strength of greater than 0.4 electron volt. It can again be covalent bond, metallic bond, or an ionic bond. And once a particular entity is formed, because it is a chemical reaction, it tends to be irreversible in nature. Again, depending on that, it might have a barrier as well. So in case of a barrier, it has to jump from physioption to chemisorption. So we will see that how this particular barrier can affect. Again, it can also have variability in terms of kinetics, depending on what is the overall barrier. It can dictate the overall kinetics of the particular process. Again, it can be again dissociative. What is that? We can come back to it. And but it is very highly sensitive to the surface symmetry, because it highly depends on if a particular atom or a species is located on the surface and there is a particular tendency to attract a particular ion or a species, then that particular ion or species will tend to go exactly at the site where it is finding much more comfortable with. So in case of chemisorption, it forms a very strong bond. So it becomes much more sensitive to the surface. So the species which is getting chemisorbed on the surface, it becomes very sensitive to the surface symmetry, and at the same time it becomes limited to monolayers, because it is so sensitive to the symmetry part or the species part which is attracting it. It becomes limited only when that particular species is available on the surface. Once it gets chemisorbed on the surface, there is no other ion which is available for it to deposit further. So once it forms a monolayer, there are no free substrate species available to again trap those adsorbing species. So that is the reason it is basically limited to the monolayers. But more than that, it can occur for a wider range of a surface temperature. So when the surface temperatures are pretty high or pretty low, it can still occur. And physioption can be a first means of leading to the chemisorption as well. So in chemisorption, we can find that we can have much more lowering of the energy of the surface, which can occur via chemisorption, because it tends to form a very stronger chemical bond. The strength of the bond is pretty high. It can be either covalent, ionic, or metallic. And once it is allowing the particular species to form on its surface, it is because of chemical interaction, the chemical reaction between the two species. It is limited to the surface only, but at the same time it tends to form only monolayers, because now once monolayer is formed, there is no freely available surface to react with the adsorbate further. So in that particular manner, it tends to form a monolayer only. But it can now occur in a variety of temperatures, because even physioption can lead to chemisorption, and even at high temperature the kinetics factor comes into play, and then again that can again lead to some formation of chemical bonds, and then it can release its energy to make the system much more stable. So we can see that it is sensitive to the initial orientation of the molecule, because once you have some species out there, some chemical species to attract adsorbate, so it will depend on where the particular species is. If I have a surface and if I have a particular attracting species for the adsorbate out here, then the adsorbate, instead of sitting here, it will tend to go and see these locations and form a chemical bond. So we can see specifically that this particular atom will tend to go and sit out here and form a chemical bond and release its energy, so thereby lowering the overall energy of the system. So second atom, it will try to go here now and form a chemical bond with the targeted species as well. So again, it can also lead to changes in the internal bonding. Because of that, it might tend to destabilize it, and it might tend to lower its energy. And again, because of this, it is also sensitive to the point of approach. So that's what we just discussed, that because this particular species is now much more comfortable or much more attractive to this particular approaching species, this becomes highly sensitive to the point of approach or the adsorption side. So that is what happening with the chemisorption part. So this is how it becomes sensitive to the initial orientation of the molecule. It might also be the case that if a particular molecule is coming like this, and my site is out here, and which can accept this particular molecule, then ideally this part has to come down here and sit more like this. So that is the reason this one becomes much more sensitive to also to the orientation. It is not only specific to site, but is also sensitive to the orientation of the particular molecule. And again, the type of bonding which generates out of it again is now much more sensitive to that particular thing. And again, we can also see dissociative chemisorption, and generally the direct chemisorption is generally not observed, because it is basically being followed by the physioption. So physioption is a sort of transient phase, and which mediates the adsorption. So it serves as a precursor to mediate the adsorption at for chemisorption. So in this particular case, what we can see is once we have a particular potential out here, and then we try to have a physiooption, then we did see that after some time, depending on how the potential curve is, we might have some certain barrier to it. We might have certain barrier to it. This is for the chemisorption and this is for the physiooption. So we can see that this is a zero potential, and it might happen that our surface is much more activated. So what we can see that the initial potential is now much higher at much higher level, but by lowering its energy, it can lower down its energy by so much extent. So physiooption will definitely try to go and jump into this particular well. So that's what we can see here, that once I am here, that once a particular species has come here and it wants to lower its energy, it has to cross this particular barrier and then jump onto the lower energy well. So it can lower its energy by this particular extent, but to overcome this particular, to basically attain this particular much of stability, it has to overcome this much of a barrier. So that can happen, that also is required to happen, that this barrier height will affect the overall adsorption kinetics, because depending on the height, what is the overall probability, it will define how is the lifetime of the transient, because it is a transient state and it has to jump to the lower energy state. So this is nothing but the transient time, and also the desorption kinetics. It might happen that this jump from here to this from point A to point B is such that it is long enough. So what can happen, it can basically get desorbed onto the surface, because this much energy it can take, and it can basically go back, or it can get desorbed from the surface itself. So the overall transient time is very important, the desorption kinetic is also very important, and the overall lifetime also of the transient is also very important for the transition from physiooption to chemisorption. So generally we see that direct chemisorption does not occur, and then this is the potential out here, this is the overall distance of the molecular surface interface. So this is the overall distance, and that is what we are seeing here. So in this particular case, we can see that we need to first of all the molecule has to go under physiooption, and then basically it has to cross this barrier at this particular junction, and then come back to the chemisorped state in order to lower its energy. So physiooption basically serves as a precursor to mediate the adsorption, mediate the chemisorption, and then again the barrier heights are basic factors in terms of dictating the adsorption kinetics, or defining the lifetime of the transient, or the desorption kinetics. It is being dictated by this particular barrier height. And sometimes it might also happen that physiooption to chemisorption may not be feasible at all. Let me go back to it. The dissociative chemisorption, it can happen like that we have a particular entity which now can go and serve, basically sit on the substrate, but later on what can happen is that it can now start chemically reacting with itself, and it can leave the surface as a molecule. So initially atoms, they go and sit on the surface, and they basically get dissociated by forming a molecule. That is what is happening. This is what is called a dissociative chemisorption, that we have species arriving as an atom, and then it stays on the surface, and then basically it leaves out depending on their chemical stability. This can happen is that that hydrogen atom, it can basically sit on a gold surface, but once it is desorbing, it desorbs. The hydrogen atom is basically coming and sitting on the gold surface, but it goes out as a hydrogen molecule. So hydrogen atom is coming, but is leaving as a hydrogen molecule. So that is what basically can happen. But in some cases, like it can happen that once hydrogen is physiorbing on the gold surface, chemisorption is exothermic. So again, that may not assist the formation of hydrogen physiooption on the gold surface at all. So in that particular case, we can see that in certain cases, the physiooption to chemisorption transition may not be feasible in certain cases, because in certain cases, like if hydrogen molecule wants to adsorb on gold surface, chemisorption becomes exothermic, and again it is basically, it is not becoming feasible, because it requires very high energy to get physiorbed on the gold surface. So in that particular case, we can see the transition will be more like this, that we have physioption which can occur like this, then we have chemisorption, but in chemisorption we have more like this kind of pattern. So we have certain energy which is much higher, so we have this barrier height which is again pretty high, so we have this particular desorption energies from here to here. So chemisorption to desorption will basically happen here, this for the desorption, but whereas for the adsorption we require such a high energy, delta E adsorption. What my molecule is already sitting here, or the atom is directly sitting here, then it may not be feasible for it to basically go from this state, the lower energy state like A to B. So we can see that in certain cases, once I don't have the dissociative thing, activated adsorption, my delta E desorption is not equal to the delta E adsorption. Generally, I can expect that this might once it is at point B, when chemisorption is occurring, once it is lowering the energy, then it makes sense for the jump of atom for the particular point, for a particular species to go from point A to point B, because it is lowering its energy. But in certain cases, when this particular desorption thing is pretty high enough, and again my delta E adsorption is even higher, so in that particular case it will remain adsorbed because it is much lowering of the energy. Like here, so we have our delta E adsorption, and the barrier height is pretty high. In this particular case, we can see the delta E adsorption is pretty high, and for desorption it is again lower, but the barrier height itself is so high that the point A may not want to go to point B, and in that case the physisorption to chemisorption transition may not be possible at all. So to define that how this particular thing, how the adsorption is occurring, we can define them in terms of what is the amount of adsorbate on the adsorbent as a function of constant temperature. That's how we get the term isotherm. So we're defining this particular relationship at a constant temperature to define how much amount of adsorbate is sitting on the adsorbent, and that can be defined by the pressure or the concentration of the species on a particular adsorbent. So if it's a gas, we define it by pressure; if it's a liquid, we define it by its concentration. So we can define it by the quantity which is being adsorbed on the particular mass of adsorbent. So to basically we can normalize it, and that thing is being defined by the pressure of the adsorbate, and K and N being the constants for the adsorbate pair, which is being specific for a particular adsorbate pair. So in this particular case, we can see that higher the quantity being adsorbed, I can get higher amount of pressure which can be the pressure of the adsorbate which can be rendered. So higher the quantity of adsorbate, my pressure is now much more higher. So that is how it basically this particular relationship comes about. But again, in this particular case, we can also define it using a Langmuir isotherm, that gas molecule will find a site and it will stay there because there are certain assumptions which are required. And again, once we have theta as the surface coverage, then the fraction of adsorbate which is now sited, it basically is now occupied at the equilibrium. So that is what we can see here. The overall equilibrium fraction, it can be basically being defined by the species of which has a direct rate constant and with the inverse rate constant, and so that it eventually comes out to be the overall coverage. This is the overall coverage. So this is the overall free space which is available to the particular species, and this is the overall partial pressure of the gas or molar concentration of a solution. So from this we can see what is the overall fraction of the adsorbed site which is now occupied at particular equilibrium. So that is being given by K. So again we can see, so this K can be defined as the equilibrium number of fraction of the sites which are now occupied. So this is defined by K. So we have a particular species of A which is gas and is going and sitting on a particular surface S to form AS, or it is occupying a particular surface, and at equilibrium we can define the overall fraction of the adsorbed sites by the overall surface coverage and the overall partial pressure which is being generated. So from this we can directly see is for very low pressures, when I have P very low, I get overall theta which becomes equal to the Kp, because once this term is very low, once it is very low, and this becomes Kp by 1, and this is again nothing but equal to Kp. But once for very high pressures, once I have pressure very high, then what happens is my this term becomes, this starts dominating, and then Kp by 1 plus Kp, it becomes eventually to be 1. So my theta becomes approximately 1 for very high pressures. So this is what this is how it is being defined by the Langmuir isotherm, that we are finding a fraction of adsorbed sites which are being occupied at equilibrium, that is being defined by the overall surface coverage and the overall pressure of the gas which is now being generated, or the concentration of the solution, and from that we can define the overall coverage. And for a very low pressures, my theta is equal to Kp, for high pressures my theta is equal to approximately 1. And Langmuir isotherm is now based on certain assumptions, and these assumptions are very like they require to be stated out here, because this forms a modeling for doing the particular for defining a particular isotherm in terms of deciding its coverage. So assumptions are that the surface of the adsorbent is uniform. It means that all sites which are required for adsorption, they are equivalent. So if a particular surface, if my particular species coming here, it has an equal probability of going and sitting on any of the sites. So this is what is being defined, that the surface of the adsorbent is uniform. So this surface of the adsorbent is uniform and all adsorption sites are equivalent. Secondly, it says that adsorbed molecules do not interact. So once I have a particular species which is now adsorbed on the surface, it does not react or interact among one another. So adsorbed molecules among themselves, they are not interacting, and again all adsorption is occurring through the same mechanism. So that is one more feature of it, that the way this particular species will go and sit on this particular site, the similar manner another species will go and sit on some other site. So they are being dictated by the same mechanism for this particular adsorption, and at the maximum adsorption only a monolayer is forming. But that again becomes a limitation for this Langmuir isotherm, because generally we define for physioption more than one layer can practically form. But for in this particular modeling, Langmuir isotherm model, we can take it only as a single monolayer for keeping the simplicity, because the way we are defining the coverage, that is again dependent on the kind of pressure which is now being generated by the surface. So that becomes a limitation for defining a Langmuir isotherm. So molecules of adsorbate, they do not deposit on the already adsorbed molecules of adsorbate, and they deposit only on the free surface of the adsorbent. So if I have a particular surface where I see the deposition of already certain molecules or ions or atoms out here, second atom, it may not see and may not sit here, it might go to some available site, and then it can follow and sit here. So that is the deal about the adsorption of a particular molecule on a free surface. So this we can see that it poses certain limitation, that we are assuming that the surface of adsorbent is uniform and adsorbed molecules, they do not interact, whereas practically these adsorbed molecules can again start interacting with one another. So that again is a possibility, but again we are saying that adsorption is occurring to the same mechanism and it forms only a monolayer, and the newly arriving species can sit only at a free surface. So to define that, we have a method of seeing how much coverage is being now done by a particular species. So we can define that by a BET technique, that is called Brauner, Emmett and Teller technique, and this is named on the three scientists who basically defined this particular isotherm in 1938. Those are Stephen Brauner, Paul Emmett and Edward Teller, who had basically developed a model for isotherm. So as we see in the previous case, we were assuming only a single monolayer to be getting adsorbed as a monolayer, but in this case we can see, we can basically classify as a network or a subroutine of it, that we can see that first we are forming a monolayer, and then we are forming a bilayer, then we are forming a trilayer. So we can see is that if molecule is already being adsorbed on a surface, then we cannot extend the Langmuir isotherm once the molecule is already now adsorbed. So BET technique now comes into picture, that it can define them as a multi-layer. We can see that there are multiple levels of adsorbents on the surface, forms a monolayer, then that monolayer comes and sits, and the next species it sits on the surface to form bilayer, and then keeps on going to forming trilayer and so on. And that is what is more practical, because it might happen that second species they can come and find this surface to be more feasible and start sitting on the surface of a already adsorbed species. So that is how it is forming bilayers and multiple surface layers. So basically we assume that gas molecules, they are getting physically adsorbed on a surface and forming infinite layers. So depending on how many gas molecules come, there is no limitation that they be restricted to certain monolayer or a bilayer. So in this particular assumption, we are making a practical case that gas molecules can come and sit on a already adsorbed surface as well, and it can form infinite layers. At the same time, there is one more limitation, that we are also assuming that there is no interaction between the each adsorbed layer. And again we are also assuming that Langmuir theory can again be applied to each layer. So this is again a limitation of that, but we are eliminating one limitation by making it a multiple layer or infinite layer adsorption on the surface. But we are assuming that these all layers, they are independent and they don't interact with one another, and at the same time we can apply this Langmuir theory to each adsorbed layer. So that is the advantage of this particular BET theory, and it basically comes out to be a formula like that our adsorbed gas quantity, it has some relation with the equilibrium pressure and the saturation pressure. This is the saturation pressure and the equilibrium pressure with respect to the monolayer which is now being adsorbed on the surface. So that is how it basically comes, and again this C is nothing but a constant which arrives from the liquefaction, and it is given by the exponential of E1 minus EL. That is nothing but the heat of adsorption which is now emitting from the first layer in order to lower the energy, and EL is for the second and higher layers. So how much energy is now being reduced by the adsorption of all these species. So this is more like a reduction in the energy of a particular surface by the adsorption, that is being accounted by the term C, and that is how it is now associated with how the monolayer adsorption will occur with respect to the pressure it is forming. So that is now being given by the equilibrium pressure to the saturation pressure of the adsorbate. Saturation pressure of the adsorbate is basically the maximum pressure it can exert, and equilibrium pressure is the pressure which is now being exerted at the under the equilibrium conditions. So this is how which can be utilized for defining the BET isotherm. So in this case we are doing it like that, we are defining a dependence of this monolayer with respect to multiple layers, and be able to give the overall saturation pressure with more and more number of atomic species. So for a particular species we are getting certain equilibrium pressure, and as we have more and more number of adsorbed species, it will start increasing the overall saturation pressure. So in that particular manner we can eventually find out what is the overall composition or the overall concentration of or the overall coverage of a particular species. So basically we can basically see is from the adsorbed quantity of the gas on the particular substrate. This is a defined quantity. The kind of pressure it is generating, the saturation pressure and the equilibrium pressure, that part is also known. So a relationship between them can provide us a particular slope and a particular intercept, and from the intercept and the particular slope we can always calculate what is the overall gas quantity which is now adsorbed as a monolayer, and again the concentration which is now basically being arrived from the initial part of the E1 and EL, that is the heat of adsorption for the first layer and for the higher layers. So from that we can always calculate the overall reduction in energy and also the overall gas quantity which is now being adsorbed on a particular surface. And again from this intercepts we can basically calculate the overall surface area, and we can also calculate the specific surface area from this particular technique. But the idea is that now we can total surface area can be very useful, because it will tell us what is the overall vacant site available in a particular volume. So that is being defined by the BET isotherm, and from that we can eventually calculate what is the overall porosity of a particular material. So once we know what is the overall free volume available in a particular material through this particular technique, we can using a particular equation of the total surface area by the monolayer which is now being adsorbed on it, V is the overall volume of the adsorbent gas, and N is the Avogadro number, and S is the adsorption cross section. So from that we can always calculate what is the total surface area, and if we divide it by the overall molar weight, we can also get the specific surface area for a particular species as well. So we can define the overall what is the overall specific surface area which is now available for a particular material. So BET comes a very handy tool in terms of defining the overall porosity, in terms of its volume, as well as so in this particular case we can see BET plot is a very critical tool in terms of being able to define a particular total surface area as well as the specific surface area to be able to calculate the overall porosity of a particular material or define what is the overall area available for a particular entity or a gas species to react with a particular surface. It is very much critical in terms of defining catalysis, because we want a particular gas or any entity to come and get absorbed on a particular surface, and higher the surface area, higher will be the adsorption, and that will be defined by the available porosity volume or the overall surface area available for the reaction. So coming to the surface adsorption, many atoms basically they can form ordered adsorbate layers on a basically lower index planes. It can again have a very defined relationship that is commensurate, or it can have just random structure which is independent of the substrate, so it can form incommensurate structure as well. Again, they might have dependence on the temperature, it might have dependence on the chemical species which is available on the surface. So it has certain criteria which is available which can happen or in terms of defining the surface adsorption. So there are certain notations which are now being developed. So one is called the Woods notation. So if we take a particular crystal of a simple cubic just showing a 100, so we have a particular unit cell of 100. So we can see a simple cubic has certainly 8 atoms on the corners of a particular crystal. So we can see one of its surface, if we take 100 and we define it by x, y and z, we can see that one of its faces will look more like this, that little atoms along x and y more like this. So it can again be defined like that, but once we start seeing some adsorbates on its surface, they might have certain symmetry to it. So this can again be defined using the Woods notation, that in this particular case we are taking this one as the unit cell, or it can also have, we can take this particular entity as a unit cell for the adsorbate. This is what we require for the substrate, this grayish portion, this is what we require for defining a particular substrate, unit cell for a particular substrate. But for defining the orientation of the adsorbate, we have to take a bigger unit cell, and from that we can see that it is defined by a simple cubic. It is more like a simple cubic structure with a 100 surface, and is a primitive lattice, which is now 2 by 2 of the original lattice length. So we can see it is starting from here, is going to 1 and 2 lattice points, two atomic positions to sit out here. So we have this atom which is now 2 atoms apart, so it is forming 2 by 2. So it is defined by simple cubic, which is now sitting at the 100 plane of the initial substrate. It is forming a primitive lattice which has a length of 2 by 2. Yes, it is going 2 in the x side and 2 in the y side. So it is going 2 unit vectors in the x side and 2 unit vectors in the y direction. So that is why it is forming simple cubic 100, and we can just eliminate the primitive word p, and we can define it by simple cubic 100 and into 2 by 2. In case we had certain lattice like that, we could also have something like this. We have an atom, third atom, fourth atom, fifth atom, like this. And then we can also see that if our adsorbates, they are sitting more like this, then in this particular case we have to take this one as a unit cell, and that will be defined by a simple cubic sitting on a 100 surface, and now it is 2 unit vectors in x direction and 1 unit vector in the y direction. So this is how it has to be defined like that. In some other case, if we can go back and say that if my atomic arrangement is like this for a simple cubic 100, and say if I had something like this, one atom adsorbate out here, one out here, one out here, one out here, I can take either this as a primitive lattice, or I can also take this as a primitive lattice. I'll definitely have to take this as a primitive lattice, which is now dotted, because this one is forming my now C centered, and this one is now my primitive. So I can define it in two manner. I can say it is a simple cubic. First I am taking only primitive case, so it is a simple cubic. Now it has to travel root 2 distance. This is to travel root 2 by root 2 at 45 degree. So I am defining it as again. Let me define as for the primitive. I take it as simple cubic sitting on the 100 surface. Now it is a root 2 by root 2 because I am traversing root 2 on this side, on the x side, and root 2 on the y side to reach the second adsorbate species. Or I can also define it as a non-primitive simple cubic 100 substrate surface. Now what I am doing, I am traversing now from here, I am going to this particular side. So if what I am doing, I am traversing from here to here, and then from here to here, it is more like the previous case. So I am traversing 2 by 2, but now this particular species has become, it has one more atom at the, one more adsorbate at the center, so I make it C centered. So I can define it by simple cubic 100 which is C center, and I am traversing 2 by 2, or it is a simple cubic 100 plane, and I have to traverse root 2 by root 2 in x direction and in the y direction. So I can define it by vectors of root 2 by root 2 at an angle of 45 degree. That is it. That is how I am defining my adsorbates using the Woods notation. I can also define them using a matrix notation. So I have the similar arrangement of them. So I can take a simple cubic 100, and in this particular case I can have A1 equal to A2. So in this particular case I can have A1 equal to A2, more like that. So my A1 direction and A2 direction, they are basically equal, as well as they are perpendicular to one to each other. So in that particular case I can define them using like that. Or alternately I can also have some other surface, like in FCC I can take a 100 surface. So my atoms in the x direction are much farther apart as compared to my z to my y direction. So I can see more like this. So in this case I will see that my A1 is much smaller as compared to the A2 direction. So I have my A2 like this, A1 like this. So I am seeing this is my A2, this is my A1. So I am seeing that for my FCC 100 lattice, my A1 is much smaller than A2. At the same time they are perpendicular, but there can be again one more case, that in some other location I can have some different arrangement of FCC. I can have AB kind of a structure. So I can see more like this type of structure, where my A1 is like here, my A2 is out here, and now my A1 and A2, they are not perpendicular but they are equal. So A1 is equal to A2 but they are not perpendicular. So again I have to define the A1 and A2 based on that. So if I take a particular other system, I can define I can correlate basically the Woods notation and the matrix notation more like this. So I am just defining the initial my substrate. So my substrate let it be simple cubic 100 surface, and if I go back and take my adsorbate species more like this out here. So I define it like that. So in this particular case I know that it is forming a simple cubic 100 surface, and I am defining my primitive lattice of 2 by 2. So similarly what I am doing here, I am traversing, if I define them as direction B1 and direction B2, and the initial direction be A1 and A2 of the initial crystal surface, the surface of a substrate. So in this case what I am doing, I know that my B1 and B2, they are dependent on the A1 and A2 by 2002 of A1 A2. For achieving B1 I am traversing 2 distance in A1, and I am achieving my B2 I am traversing 2 distances in A2. So that is how it is equivalent to this. This is a matrix notation, this is a Wood's notation. Had I had some other geometry, so in case I have some other geometry, so had I had a particular different geometry, so let me take it more like this. So say my adsorbate atoms are out here, out here, out here, regularly placed like that. So how I can define them? I can define them by B1, B2, but in this case my A1 and A2 are again in the same direction. This is my A1, this is my A2 direction. So this I would have defined by utilizing primitive lattice of defining them as simple cubic 1 0 0, and again it was forming my primitive root 2 by root 2 R45. Now I can define that through my matrix notation more like that in case my B1 and B2, now what I am doing, I am traversing one distance in the x, one distance in A1 and one distance in the A2 as well. So I am defining it by 1 1 A1 A2. Similarly for reaching here I am traversing minus 1 in the A1, so minus 1 in the A1 and 1 in the A2. So this is what is the matrix notation for this particular system, and this is the Wood's notation for this particular system out here. System or the matrix notation for defining the way adsorbate is sitting on the adsorbent, and for that we can use a very simple Wood's notation or a matrix notation. So we can play around and we can see how it is to be defined. And so just to give you an equivalent, if I am taking a nickel substrate, taking a plane of 1 1 0, it can be C centered, and defining how much distance I have to travel, so 2 in A1 and 2 in B2, and we can also define an adsorbate which is sitting on the substrate. So again just to give you equivalence, I can traverse more like that I am defining a platinum surface of plane 1 0 0. I will traverse 2 root 2 in x and root 2 in y at an angle of R45, and the adsorbate is again oxygen. That means equally I am in matrix notation, I have a similar plane, but now I define this particular part as traversing 2 distance in x, 2 distance in y, and minus 1 in x, minus 1 in y. So these terms become equivalent. But one very important criteria which separates, which basically is not at all available, and we tend to think that it is, that neither the Wood's notation or not the matrix notation, they will tell us anything about where the actual adsorbate is. They just tell us how this adsorbate is now oriented. Had I had adsorbate like here, or maybe like here, I won't know what is the difference between these two. It will define both the Wood's notation as well as the matrix notation will define them as the same. It won't differentiate whether it is on a particular or exact location. So again it depends on the nature of the bonding to the surface. It might happen that the non-directional bonds, they may result higher symmetry because they are not at all, they don't have any certain direction. So atom can go and sit anywhere, and because of certain repulsion among itself, it will tend to achieve a very high symmetry. But in case of directional bonding, it might need to go and sit exactly at a particular location. So it will limit, basically there is some restriction. So that is what it might create a low symmetry bridges on the top side. So that is the overall deal with the definition of the adsorption on a particular substrate. So in this particular lecture we did see that how we define a isotherm, that we initially assume it to be a monolayer, but then we can go on defining it in terms of bilayers and trilayers. So we extended our initial isotherm to making it multi-layers, and then assuming that these layers which are now multi-layer, they don't interact with each other, and they have basically form uniform layers, and then they go on to forming multi-layers. And from that we also see that how physiorption and chemisorption tends to basically affect how this particular species is now getting dissociative, or how it is getting attached to a particular surface. And then we also learnt about how we can utilize this matrix notation and Wood's notation to basically say where the particular adsorbent is sitting on a particular adsorbent surface, and how we can play around with it. But these techniques don't tell us exactly where the particular adsorbate is sitting. It only tells us how they are basically sitting. So I end my lecture here. Thanks a lot.